Now you know when you move your hand through the water slowly, you feel some kind of resistance. If you move your hand through the water a little faster, you're going to feel more resistance. You're essentially moving more water out of your way, creating maybe a little more turbulence, etc. So that the force you feel increases with your velocity, with the velocity of your hand. Now, if you don't move your hand too fast, that force tends to increase pretty much linearly with the velocity. And that's called, I'm talking about water, but we're not, it's called damping. It doesn't mean that to get your hand damp, it means that it damps the motion of the system. It damps it down, it interferes with the motion and puts limits on what can be done. Ultimately, a damping term will use up all the energy you've got available if you continue long enough. So the damping term that we're going to add is I'm going to call it 2 delta y prime. Remember that y prime is the velocity, and this is then just a multiple of the velocity. Now, in general, we can write the net force on a system which is damped by some force that's opposed to the motion of the object, so that the force acts in the direction opposite the motion. And our my double prime, which is our force, mass times acceleration, will then be negative ky, a restoring term, the restoring force, the force that tends to restore the system to equilibrium, being a linear function of y with some constant k, and we're familiar with that. And then we have our damping force, and I'm going to call that some damping constant times y prime, some damping constant times the velocity. And then our driving force, F cosine of omega naught t. Now we're assuming that we do have a driving force that's resonant with the system, a driving force at the same frequency as the natural frequency of oscillation. And we're going to identify our C damping with our 2 delta. These things mean the same thing, and I'm using 2 delta here just for convenience. It's just going to make the arithmetic or the algebra of solving our equation a little simpler to have a 2 in front of our constant. So our damping constant is 2 delta, and now we can rearrange this equation, bringing all the terms that have y or derivatives of y onto the left-hand side, leaving our non-homogeneous part, our driving force, on the right-hand side. Formally, I'll say that 2 delta is actually just our damping constant divided by the mass. So that when I said before that these two were identical, they're not quite identical. We've got this division by the mass. This is something that your book doesn't always follow, and I have no objection to that. Those guys know their field better than I know mine, and they certainly know the differential equations a whole lot better than I do. So I'm certainly not going to debate with them. I'm simply going to follow my preference with my foot in both worlds, the mathematics and the physics, and try to be very clear about exactly what this means. Okay, so in any case, the damping force is then going to be 2 delta times m y prime. And when we then substitute that for C damping and divide by the m, we do end up with a 2 delta in front of y prime. If you're keeping track of the units of these quantities and the meanings of the quantities, again, I think better off to make sure we understand where the mass comes in. In any case, and as we've seen before, omega naught is the square root of k over m. So that instead of k over m in front of the y, and of course again if we divide by the y we get the k over m. Instead of a k over m in front of y here, we're going to call it omega naught squared. The solution of the homogeneous equation is very simple, our characteristic equation, and actually I have to admit I've been a little bit careless about the use of the term characteristic equation. I'm kind of taking this homogeneous equation, and I've been calling that the characteristic equation, whereas the characteristic equation, look there, there's another exponent 0. I'm going to just slop that one down. I can change that to something that kind of looks like a 2 without going to a lot of trouble. Okay, sorry for the digression, but we have our characteristic. This isn't really the characteristic equation. This is. But in any case, our homogeneous equation has a simple solution where r is negative delta plus or minus the square root of delta squared minus omega naught squared. Now there's no reason to suppose that one of these terms, delta or omega naught, is greater than the other. But well, there's really no but about it. In some cases, delta is going to be bigger than omega naught. In some cases, omega naught is going to be bigger than delta. If I have an oscillatory system with a certain omega naught, whatever's dragging on it could have a bigger or smaller effect. So this delta could be bigger or smaller than our natural omega naught. So if delta happens to be bigger than our natural frequency, natural angular frequency omega naught, as you know, that's going to give us two real solutions. If delta is bigger than omega naught, then we have a positive under the radical, and we get two real solutions: negative delta plus the square root and negative delta minus the square root. And I've simply written that down here. We have a solution set e to the quantity negative delta plus the square root multiplied by t, and e to the quantity negative delta minus the square root, all multiplied by t. And these solutions are kind of dull. They don't oscillate, although they can lead to behavior that crosses the line and then comes back. But we also have the possibility that delta is equal to omega naught, that our drag force is just at a certain critical value where it happens to be equal to omega naught, that is our drag constant. And that results in the radical being 0 and our root to the characteristic, algebraic characteristic equation being repeated. And as you remember, that leads to solution set e to the negative delta t and t e to the negative delta t, originally arrived at by reduction of order argument, but sort of evolved into a rule of thumb. Most people forget the reduction of order argument and just remember to slap a t on when you have a repeated root. I mentioned the reduction of order argument just to remind you that there really is a reason for putting that t there other than just that it works. The most interesting case is where we have the two complex solutions. So our solution set is going to be e to the negative delta t times the sine of the square root of omega squared minus delta squared times t. And notice that this reverses the order of the omega naught squared and the delta squared, because when delta is smaller than omega naught, we get a negative under the square root, so that we're going to have the square root of whatever the magnitude of that is times I, and the I is used to get the sine and cosine using the Euler identity, etc. And the value that we use here is the square root of the magnitude of whatever's under the radical. And the magnitude, of course, has to be positive so that we reverse the order of these two terms. There are all kinds of ways to understand that. But the point is that we end up with our solution set e to the negative delta t times the sine of that square root times t, and e to the negative delta t times the cosine of that square root. And that square root is going to be the angular frequency of our ultimate oscillation. That angular frequency is going to be a little less than omega naught due to the delta. The closer delta is to the omega naught, the slower the oscillatory frequency of the damped system. So that if we're if we have a system that with no damping would oscillate at a certain frequency, if we then add something to damp the system, it'll oscillate a little more slowly, and of course it'll dissipate energy, which is the e to the negative delta t factor, giving us some sort of oscillatory solution that, as t approaches infinity, approaches zero. Okay, this is the solution to the homogeneous equation. We haven't yet talked about the forcing function. We haven't talked yet about solving the non-homogeneous equation, but that's where we're going to go in the next clip.